relative to the capillary. The capillary is experiencing water loss in this orange side, and in the black side, our capillary is experiencing water gain. Now, what side's bigger? Which is generally going to have a larger effect, do you think? Water loss or water gain? Or do you think they're equally balanced? There's generally more water loss, right? There's more water loss than there's water gain. In fact, because of this phenomena, you lose about 3 liters a day of water. So what do you think happens? Do you think that water just leaves us? It's no longer part of our cardiovascular system? We don't necessarily replace all of it. How do we get it back? We don't think it. We have a lymphatic system for that. So we have, it's not supposed to be orange, it's supposed to be green. We have lymphatic vessels, in this situation lymphatic capillaries, that absorb this water. And this is what part of the job of the lymphatic system is about. Part of its job is to take this water loss, absorb this water loss, so there's going to be these lymphatic capillaries at the site of these capillary beds. So at every capillary bed there are going to be lymphatic capillaries that their job is just to absorb this excess water loss. They take this excess water loss, they kind of clean it for foreign objects, foreign organisms, and they dump it back into the venous circulation. So they'll dump it back close to the superior vena cava. And so that's the main job of the lymphatic system, is to kind of counteract this water loss we see at our capillary beds. Make sense? Alright, this is all I had for cardiovascular system. We're going to move on to the respiratory system. Any questions about the cardiovascular system before we move on? You have a question? No, are you sure? Alright. Come on. Alright. So the respiratory system. So the respiratory system actually works close in tandem with the cardiovascular system. That's why we kind of present them, we kind of juxtapose them, so you learn about them one after another. And it's because, the respiratory system is all about gas exchange, making sure you bring in enough oxygen and then release enough carbon dioxide. That's the whole point of the respiratory system. But to do that, it heavily relies on the cardiovascular system to transport these gases. And so the name of the game here is all about respiration. Respiration is really what it is all about, is just an exchange of gases. Particularly carbon dioxide and oxygen. And so generally we have 2 types of respiration happening on our body. So we have cellular respiration, so the exchange of carbon dioxide with oxygen at the cellular level. So that's one thing. And then we have external respiration. So external respiration is all about taking those gases that were exchanged at the cells and then moving it out through the body so we can exchange it with the environment. So up here is the environment. So I just mean the air around us. All this air here, we're exchanging with that air. And so there's a lot of steps to the external respiration. This is where we're going to focus most of our kind of efforts at for this next lecture today and tomorrow. And so here we have our environment. So the first part here is what we call ventilation. Ventilation is the process of taking air from the environment and putting it into our alveoli, so it can exchange with the blood. The next part is the perfusion part. Exchanging these gases with the blood itself. And the next part is, the transport via blood. And that's kind of why the cardiovascular system is so important to respiratory system, because respiratory system really relies on the circulatory system to bring the gases to the tissue. We can't just have, gas diffuse from our alveoli and expect it to reach all our tissue. We need a circulatory system to bring it there. And then the process repeats. This process happens every time you take a breath in and every time you exhale. It happens every single time. And so that's where we're going to really kind of, focus our efforts in learning here. But before that, just like the cardiovascular system, we got to learn some mechanical principles. These are principles we call the gas laws. These gas laws have some similarities to our fluid laws about flow and things like that. So you'll see some similarities, but don't necessarily kind of interchange one of them per se. One note I want to make here, I'll do it in a red color so it's obvious. Carbon dioxide does not correlate with oxygen. Very often do I see people say, oh, because carbon dioxide goes up, oxygen must go down. There is actually no reason why one needs to go up versus the other goes down. Now, there's a lot of places, there's a lot of situations where they do seem like they're correlated, but the actual two gases don't interact with one another. There's mechanisms that revolve between both of them that balance the two. So our cells take in oxygen and put out carbon dioxide, but there's actually no mechanism between oxygen and carbon dioxide that have them interact with one another. So be careful when you try to explain these principles to yourself. Don't say because if oxygen goes up, carbon dioxide must go down, or vice versa, because that's not necessarily true. Sometimes that'll be the case, but that's not going to be true every single time. And it's because these two gases don't interact with one another. There's no intrinsic connection between the two gases. All right, back to our mechanical principles here. So our first mechanical principle here is the Dalton's law. So Dalton's law is pretty straightforward. It's the idea that if you have a total pressure, so let's say, our total pressure is, let's say let's make an easy number. 100 millimeters of mercury. That's our total pressure. Then the partial pressure of any gas is going to basically be the total pressure of that gas times the percent of concentration. So for example, if our total pressure was 100 millimeters of mercury, our partial pressure, which is represented as big P and then little O2, would be 100, and then we can look at this diagram right here to show us this is the composition of gas that we're breathing right now. So it says that 21% of the gas we're breathing right now, the air we're breathing right now, is 21% oxygen. So we multiplied this by 0.21, and that tells us that partial pressure of oxygen is 21 millimeters of mercury. This is basically saying that the total pressure of any gas is made up of the partial pressure of each gas combined. That's another way of saying it. So you take the partial pressure of nitrogen, take the partial pressure of oxygen, take the partial pressure of every other gas, add them up, that's your total pressure of your whole air. So it's kind of this additive effect. And if you take this, let's say we take this air and we increase the pressure. Some way we increase the pressure of this air. As that pressure, the total pressure of that air goes up, all the partial pressures also go up with it too, because they're all proportional to the total pressure. Does that make sense? That's going to be really important. That's actually really important when you change altitude too, because when you change altitude, the pressure changes. And I'll show you an example of that in a minute. Alright. The second law, perhaps maybe even the more important law here when it comes to at least external respiration, just ventilation actually, is Boyle's law. And Boyle's law states this, that the pressure in state 1 times the volume at state 1 equals the pressure at the state 2 times the volume at state 2. Now, that could be really confusing, but let's kind of break it down as kind of a in this picture right here. And so let's say this is state 1. State 1 has a pressure of P1 and it has a volume of V1. What we do is we take this piston and we just push it down. That's what happens here. This is state 2. Now, what happened to the volume? Did I increase it? Did I decrease it? Did I keep it the same? I decreased it, right? I basically took the volume of this container and squished it, right? That's what the piston does. It kind of makes a smaller volume.